Okay, so last class we saw how to implement a list in a more efficient way using this singly linked list or doubly as well. It's the same thing. So what we saw, the important thing was this insert code, the pseudocode for insertion at a location P. Right, so when you are given P, you are also given P dot previous or P dot left, which is in this case T, and you create a new node at Q. And this is what you will insert in the middle of T and P. Okay, so this is now a very fast insertion algorithm. Same thing with delete. So we got this slide. Right, so everything is constant time except search. Yeah, so except search, everything is order 1 here. So search also we want in the directory case, that also we want to be faster. Right, so that is what we'll do next. Any questions? So in the array case, when you store a telephone directory as an array, you can keep it sorted and then you can do binary search. So you can search in login time when the directory has n entries, n records. So same thing you now want in the world of link. Okay, so in linked list implementation of the directory also you want login search time, and insertion should be as fast as possible. So how do we get the best of both implementations? Any ideas? So of course you have to maintain a sorted linked list. Otherwise you cannot do binary search. Right, so you have to maintain this sorted. So in the linked list implementation, if you try to do sorting every time you insert, what do you think will be the complexity? Right, so the code that we showed here for insert, this orange code, this needed it had many problems. It needed, first of all, a location, P should be known, where you want to insert. Now the starting point itself will be unknown. If there is already an existing directory and a new name comes, then where will you insert that name? Right, you have, the only way is you look at the whole directory and then find P and then do this. So that is order n. So that you cannot, that doesn't help. So this will require, so insertion will again take order n in this type of linked list. Okay, so how do we get around this problem? How do we keep the linked list sorted and still get almost order 1 in both the important operations which we are interested in a directory? So first observe that to do binary search, what you want is the middle pointer, right? So what we want is to do fast search. Let's say in the linked list, all we need is pointer to mid. So if we knew the pointer to mid at every stage, then we can just go to the mid, compare that with x, and that will tell us which side to move. Then on that half, again find the mid, and so on, right? So all you want is actually a pointer to mid at every stage. So which is, so we can store that. I mean, you have to store that then. So you augment your list implementation with head pointer, but also a mid pointer. So we can draw this suggestively like this, meaning that we have now head like before, but we also have mid. And then this ends. Okay, so mid also has to be remembered now in this pointer implementation of the list. But that is not enough, because so now you can compare x with the mid, and if x is less than mid, then you have to go. I mean, if x is equal to mid, you have already found the place. But in general, x will be less than mid or greater than mid. So if it is less than mid, then you have to find the mid of left, right? Which again is a problem. So that also you have to store. So next we need the other mids. So let's also store that then. Yeah, let's not draw this. Okay, maybe like this. So the pointers that you have now are, let's say this is head. This ended the list. This is your mid, which was stored before. This is mid 0, and this is mid 1. Okay, so gradually to do binary search, this is how the I mean, the concept is that you have to know a number of pointers to the head, pointers to the mid, then pointers to the left half mid, right half mid, which I'm calling mid 0 and mid 1 respectively. Right, so if we keep doing this, what do you get? Yes, you need pointer to every, but in a very structured way. It has to copy binary search algorithm. So the concept here is that whatever binary search was doing, it is actually suggesting you a new data structure, and that is the structure which we call tree. Okay, so this is the tree data structure, because an alternative way to see this is that you have something like this going on. So this is mid in a way. This is mid 0. This is mid 1, and so on. Okay, so if we now focus on, instead of the data, if we focus on the pointers, then this is the alternative structure which we are following. So we start with the mid. I mean, we actually, in the list, we started with the head, but head is of no use in a sorted list, right? You actually want to go to the mid and find out which half. So mid is more important. So forget the head. You start with the mid, which is now this green circle that is called the root of the tree. And then based on the decision, you either go to mid 0 or mid 1 and so on. So do you see the equivalence of these two pictures? So this left-hand side is called a tree, while the right-hand side is we are doing binary search on a linked list with extra pointers. So yes?
How would an insertion look like on the tree?
No, you are jumping too far. For that, we'll need many classes. Today, we will only show you this picture. So the implementation of this is not easy. There will be exercises for you to implement this in C. Because this is a whole new data structure, which is, a real life tree grows from the root upwards, while our tree here will grow downwards from root, right? So it's an inverted real tree. So this we call a binary tree. So this is the new thing we have invented now. So binary search gives us the invention of binary tree. So this is a new data structure, one of the most important ones in computer science. Okay, so it looks like it's an inverted real tree. So inspired from that, we call this the starting circle, we call that the root. There is only one root. It's the analog of head in the linked list case, but it has a very different behavior. Head did not have, you cannot go left of head, but here you can go in both the directions. So this will be called the root, and the root pointer basically gives you an access to the whole data structure. The whole tree is accessible from the root, right? So just one address, and then from there you can derive all the other addresses by traversing this tree. Computation happens from following the directions in the edges. Okay, so computation or your pseudocode will run top to bottom because it has only access to the root. So from there you have to deduce other things. So it goes from top to bottom. In the linked list case, we were kind of moving left to right. Here we'll move, in all the pictures, we'll move from top to bottom. And so if you keep moving to the bottom, where will you stop? Yeah, some node where there is no children, right? So that is called a leaf. So you have root, you have nodes, you have edges, and you have leaves. Okay, so those will be the new language in this class. So so let's just draw that one example. So this is the pointer to the root. This is all you have. and the tree is, let's say, T. So the data structure variable is T, which basically, so root of that is, or you can say T dot root is what gives you the root of this tree. And so there will be, so these things are pointers. So this will be, well, let's first set the terminology. So binary tree has root, edges, nodes, and leaves. Okay, and each node has these useful information. So if node is a struct, you want minimum 3 values in it. So one is the value which is stored, which is, let's say, x. Right, so it may have x here, and 2 more because you want pointers to the left and to the right child of that node. So each node will store a value. I mean, the value can be integer, it can be anything, right? The value can be a different data structure itself. It can be an array. So we don't get into that. So the information is stored, which we are calling value. But 2 more important things are needed, which are pointer to left and pointer to right. So again, syntactically very similar to what we did in doubly linked list. You had left and right, but here this has really become 2-dimensional. Okay, the linked list seem to be 1-dimensional. For this, you need 2-dimensional space to actually make sense of what we are trying to do. It is not 1-dimensional at all. Okay, it has all these directions available now. So it is something much more complicated than an array or a linked list. So we use a different term, we call it a binary tree. Okay, in any node, in every node, what is the number of incoming edges? Well, not necessarily 1. Root has 0. So the incoming edges can be 0 or 1. When the number of incoming edges is 0, that is the root. And when it is 1, then it's somewhere other than root, it's an internal node. It's called an internal node. What is the number of outgoing edges? So outgoing edges can also be 0, which means that it's a leaf, right? From there you cannot go anywhere else. It can be 1 and it can be 2. It cannot be 3. Okay, so since it cannot be 3, these are which is why we use the term binary. If it was a ternary tree, then it can be 3. Okay, so for degree D tree, it can be D, but we will not care about that in this course. In this course, binary will be more than enough. Everything can be done with binary, which you can do with higher outgoing edges. So outgoing edges, 2 means that, or 0 means it's a leaf, 1 means it's not a leaf. because you can go forward from there. And yeah, 2 is similar. So 1 and 2 refers to internal nodes, not leaves, but it can be a root. Okay, so these are the properties that define your tree. So what are the objects that are not trees?
So a value, can you explain this? Each node stores a value pointer to the left and a pointer to the right.
Value is just the data that you wanted stored, like name and telephone number. So a value and a pointer, and to the left and a pointer to the right. 3 things. It has 3 things. I mean, these are the 3 minimal things. If you remove one, then you don't have anything interesting. So there is a record which you store in the circle, which is X, and then you have to store pointers for traversing the tree structure. Is this clear? Any questions about the definition of a binary tree? Because from here on, it will only get more complicated. So you should make sure that you understand this.
So maybe you should like explain how the structure arose of the binary.
Well, this definition gives you all the structure you will need.
Like from the linked list, how did you get the bits?
Oh, no, that was just a thought experiment. This is just to motivate how binary search potentially proposes a new data structure. But once the definition is given, you can forget all this. It won't be used. So now, so once we are at this stage, this is a data structure which is completely new. It's not an array, it is not a linked list, it is not a list at all. So it's a different ADT. Okay, this is a different abstract data type, which we have not completely defined. So we have defined how it looks, but we have not defined what it will do. Right? So how do you insert, how do you delete, how do you search, and so on. In fact, not only these operations, you can have more operations. So we have not even defined the collection of operations that this affords. And of course, then there is the question of time complexity. Why was this needed? Is this faster? Is this slower? Does it use less space? So those things will unfold when the time comes. So now is the time to see whether you actually understand the definition. So what are not trees? So, for example, this structure, is this a tree?
No.
Why not? Number of incoming edges is 2, right? So because of this, there is a problem. So incoming edges 2 means that this red node you are able to reach in 2 ways from the root, right? So if any graph, I mean, if you have seen graph theory in math courses, in any graph, if there are 2 ways to go from vertex S to vertex T, then this is like a cycle. I mean, this is a directed graph, so here you don't actually have a cycle, but if we remove these the directions, then you actually get a cycle. So when you have a cycle, you don't have a tree. Okay, tree. Another definition of tree in graph theory is a cycle-free graph, undirected cycle-free graph. So coming from there. So these things have a problem of reaching in 2 ways. In tree, there should only be a unique way to reach. So this is not a tree. So what about this? No, this is a tree for sure, but this is not a binary tree. Okay. And what if you are reflexive? You have an edge to yourself. Is it a tree? Why not? Seems to satisfy everything. Yeah, so this is a philosophical issue, whether this is a tree or not. In this course, we will just resolve it by saying it's not. Because again, the problem is that there is a cycle. So you can keep calling yourself for infinity without getting any resolution. Right? So these things we don't want to call them trees. So this is not at all a tree. This one is tree but not binary. And this one has a loop. Okay, so hopefully this tells you what binary trees are and what they are not. And for pseudocode purposes, we'll need more systematic functions. So let us define that. So technical terminology for pseudocodes that we'll use. Yeah, so without even explaining, we'll use all the time terms like parent, child, left child, right child. So this will need some explanation before. And subtree. And height of a tree. So this, what parent will mean is, what is the parent of V? Yeah, that's what it will mean. So parent of V in this tree is U. This tree, let us call it T. What is the child of U? Yes, so child of U will generally be a doubleton set. So here it's X and V. But we can also say that child of U is X. So to make that precise, will call it left child. So left child of U is X and right child of U is V. Yeah, I don't have space left here, but what is the subtree of V? So the subtree of V is whatever follows, so V and whatever follows V. Okay, so that object is called, so that is again, I mean, this is a recursive data structure. So wherever you are in this tree, you only see a tree. Okay, so if you are at when you move from root U to V, V is also a root of some other data structure. So that is called subtree of V. Okay, so there is a strong, this is a heavily recursive self-referential data structure. So that you can see when you look at the subtrees. So this is the subtree of V. And similarly, the other thing, dotted thing is subtree of Y. So in that subtree, the root is V, right? And the leaf is Z, which is also a leaf of the original tree T. Okay, what is height? So height of a tree should be, well, depth is again undefined. How do you define it programmatically? Say you have to write a program to find, you are given the address to the root and you have to find the height.
And this is the longest path to reach a leaf.
Right, so the farthest leaf, that gives you the height. So distance from root to the farthest leaf. Okay, that's called height, which can also be called depth of a vertex. Similarly, so depth, or well, not depth. Let me continue with height. So height of a vertex V is just distance from V to the farthest leaf. So height of V here is just 1, right? And height of Z is 0. Height of X is, right, so you can see, so this is a height 3 tree, because height of the tree is equal to height of the root, which in this case is U, whose height is 3, and so on. So X has height 2, Y has height 1, R has 0. So height 0 ones are the leaves. And depth also can be defined, it's the opposite. So depth of V is just the distance from root to V. Right, which in this case is, depth of V is also 1. Okay, so you have depth and you have height. So height of the previous tree, for example, is 3, while height of the vertex V was 1, which is the same as the depth. And
So what would height of Q be?
height of Q, yeah, so what is it?
0.
So Q is a leaf. So what is the farthest leaf from Q itself? That is 0. And what is the depth of Q? Yeah, depth of Q is 2. So, well, height plus depth may not be height of the tree. Okay, you have enough examples. It's not that their sum is the height, but what is the result? What can you say for sure? For all nodes V in a tree, height of the node plus depth of the node is, what can you say? Yeah, this will be less than equal to the height of the tree. So that's what is true, and you cannot say anything more than this. Okay, one more example. So what is the height of the subtree of x? So look at the subtree of x. What is the height of that? That is 2. Okay, which is again a trivial property that height of, for all nodes V, height of the subtree of that node is equal to what? Is equal to height of V. Fine. So height of a subtree is also height of that node. These are trivial things from the they follow from the definition.
So but the depth of the subtree of V is going to be 1.
Depth of which one?
Subtree of
In this example?
no, sir. With reference to this figure, depth of the subtree of V is going to be 1.
Yeah, so when you look at the subtree, then you have forgotten the main tree, bigger tree. So what you are asking is, what is depth of the root?
It's going to be 0.
Yeah, depth of the root is 0. So height of the root is equal to height of the tree, and depth of the root is 0. So height of the root plus depth of the root is equal to height of the tree. Okay, so the first inequality is actually an equality when you look at the root. Other than that, you cannot make big claims. Okay, any questions here? So that is the setup. Now, is array a tree? Excellent. So what is the height of the array? So an array A having n elements, right? This is also a tree because after all, it can be seen as just in 1D. So there is 0, there is 1, there is n minus 1. And A is pointing to the root. Right? So the computer organizes, or the OS organizes the array as this, equispaced addresses, right? N addresses. So this is a one-dimensional tree. So an array is also a tree. It's in fact a binary tree. With height equal to, is it n? N minus 1. Right, so array is also a binary tree with height n minus 1. So in that sense, now both linked list and array have been subsumed inside binary tree. Right, so this is a more general, more expressive data structure. So where will the advantage come from? So just saying binary tree will not be enough, because binary tree also contains these bad data structures which we wanted to go away from, right? So any ideas? Right, yeah, sure. Singly linked list is kind of an array it's surely a binary tree. So these kind of instantiations of a binary tree, we call them skew binary tree. So this word skew, if you don't mean what this in English, what this means, it basically means that I mean, at every when you go to any node in this binary tree, which is drawn in orange, there is no. I mean, there is a imaginary option here which is left unused. Right? This also should have been used. So binary tree gave you the option that these green edges also should have some subtree sitting there. But you have not used it, so basically that subtree is 0. So out of 2 options, all your options at every stage are skewed only in one side. Okay, so this is a tree which is always favoring its right child and ignoring the left option. Right, so such data structures or such instantiations of tree are called skewed because they are not using the 2 options which are available. Because at every stage or at every node, one child is missing. So what this leads to is too high, so the tree is too high, height is quite high or maximum, and consequently it's too thin. Okay, so this is what the problem with these arrays and linked list is that the height is very high. It's maximum possible, which is n-1. So we want to get away from that. So we want to move from 1D, as I said, to 2D. So we have to use the other dimension. So we have to make it fatter in that dimension. So to make it fatter, the term that we will use is balanced. So this will be an important concept which will give you the exact data structure that you needed. So a balanced binary tree should be what, in your opinion? Yes, so what will you get if you had 2 children at every node? That is something very special. No, so like the example I drew first. So this has 2 child at every node, but so for a given n, how many such trees are possible? If your number of nodes is n, how many such trees that you are suggesting are possible? Are there 2 trees that are possible? I mean, yeah, up to some symmetry, you have more options, but in a way, so for example, if you count the nodes here, you are getting 7. So it will always be of this type, 2 raised to k minus 1. Okay, so if you forced every node to have 2 children, then the number of nodes you will get is 2 raised to k minus 1. So you will get this 7, or you will get 15 and so on, 31. So your options will be very limited then. Then you will be looking at only one data structure. So that's not a good definition. So those things are called complete binary tree. Okay, that's much more than balanced. So maybe I'll give that as an example. So, but here in balanced, we will use something more sophisticated, which is that the left subtree size and the right subtree size should be almost the same. So a balanced binary tree, the property will be has every node x or v such that the not the size, sorry, the height of the left child of x minus height of the right child of x. This difference should be not more than 1. Okay? So balanced in terms of not how many children or how big the subtree left or right is, but simply in terms of the height. So for example, in the case of array, when you are at 1, what is the height of the left child? That is 0. I mean, there is no left child. And the right child height is n minus 2, right? So the problem there was that the difference in height is too high. In nice examples like that complete binary tree, the heights are always equal. So again, you can see that example. So this example is nice because here when you look at a node like x, both the heights of the children are well, 0 in this case, and the height of the in the case of the root, the height of the left child, right child is 1. Okay, so the differences were 0. But for algorithmic reasons, we are allowing some leeway, so the difference can be up to 1. Equal would give you, if it was always equal, it will give you complete binary tree. If it was sometimes equal and sometimes 1, then you get very different looking trees, binary trees, but they are all balanced. What is the advantage of this? We will see in the next class. You can prove a major theorem which will give you fast algorithms. Okay, let me correct this mistake. This is V. So height of the left child of V and height of the right child of V are almost the same. That's what we are saying. So yeah, we don't have time left. Let's just see some examples. So So would you say that this tree is balanced or unbalanced? Yeah, so that only way to check that is write down the heights of the children. So here the heights of the children are 2 and 1. What is the height here? 0 and 1. I think it will be a bit better if I said left subtree instead of child. Because this child may simply not be there, then it becomes vacuous. So height of the left subtree and right subtree. Okay, so we are looking at the subtrees, left or right, of every vertex. So let me update these numbers. So now the left subtree is, actually you get the same number. It will still be 2 and 1, yeah, that was correct. And here it will be 0 and 1. Here it will be 0 and 0. Leaves, anyways, vacuously this condition holds 0 and 0. This node is the only interesting node, so here you have also 0 and 0. Okay, so you can see that the left versus right subtree heights are always, they always differ by 1 or 0 in all the cases, right? So this is a balanced tree. Yes.
The last node that we wrote, there is one more node.
Sorry?
So the last node that you wrote,
Uh-huh. Yeah, the bottommost one, if there is another child, yeah, so then you will have subtree height 1 versus 0. That's also fine. So, yeah, so you have to recalculate that. Yes, I think the problem will be, okay, maybe we just draw that. So what will happen if you drew here one more? What happens then? What is the problem? So now look at the root. Or in fact, look at the one where I've written 0, 1. So that will become 0, 2. So this will mean is unbalanced. And binary. Okay, so this is the change which happens if you add things, if you insert nodes arbitrarily, then a balanced binary tree will become unbalanced, may become unbalanced, right? Because there is a counterexample node now.
a skew tree with 3 nodes is balanced.
Yeah, so we can see those examples, but I think the class is now up. Let's do it offline. If you have any questions, you can meet here.